Hi, this is Stephen Brower from Merritt Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. In Stallings Chapter 5, one of the things that we'll look at is Hamming code for error correction. A different video goes through the overview of Hamming code. What this video is intended to be is taking the example, in other words, using this data set, calculating what the check bits would be using Hamming code. So remember, the idea behind it is if we have 8 data bits, there's going to be 4 parity bits, the check bits that will be used. Those 8 and 4 would have 12 positions, and then based on those positions, we figure out that the check bits would be those whose position number only has a single 1. So position 1, so 1 as a 4-bit number, 0001. So that would be a check bit. That would be check bit 1. Position 2, which has a 1 in this position, that would be check bit 2. Position 4 only has a 1. So this would be for check bit 4, and this, which only has a 1 in the position number, then that would be for check bit 8. The remaining positions that would be filled in with the data, D1, which is going to be the rightmost value, is here. D8 is the leftmost value, that is here. So the data and the check bits are sort of interleaved together. What I'll try my darn doodliest to do is, let me just change my font color, is just show where the data bits, so we would have 1, then data bit 0, or this one here, 0, 0, data bit 4 here is 1, and then these 4 bits are the left 4 bits, so 1, 1, 0, 0. Okay, so we've laid in the data bits into where they're going to go. Okay, just do a slight pause. Okay, so let's move on to figure out how do we calculate check bit 1. And yeah, the formulas are there in the book, and yeah, you can just go and memorize and use the formulas. But what I'm going to do is kind of show how we figure out how to get to those formulas. So if we're working on check bit 1, in terms of its position, there's a 1 in the rightmost place. So for all of the data bits that have a 1 in the rightmost place, for those data bits would be included for figuring out what check bit 1 is. And so what I'm painstakingly doing, because I have no artistic ability whatsoever, is trying to highlight so that the 2 to the 0 position, the 1 in the rightmost position regarding the position number, is saying which data bits are going to be included. So check bit 1 is going to be, I'm simulating what we would do in the classroom. It's and let me just write the formula just as a reminder first. So data bit 7, exclusive OR. I'm going to do the short notation here for exclusive OR. Data bit 5, exclusive OR. I'm ignoring that. Data bit 4. Data bit 4, exclusive OR. Data bit 2, exclusive OR, data bit 1. Okay, so that would be the formula for check bit 1. Let me go and fill in the bits. So data bit 7 is 0. Okay, so 0 exclusive OR. Data bit 5 is 1. exclusive OR. Data bit 4 is 1, exclusive OR. Data bit 2 is 0, exclusive OR. And data bit 1 is 1. Now, there's a fast way to figure this out, but let me just go left to right. And actually, you know how A plus B equals B plus A? Well, A exclusive OR B equals B exclusive OR A. So it doesn't matter if you go left or right. It also means that if we were representing the formula, it doesn't matter if we said check bit 1 is data 1, exclusive OR data 2, exclusive OR data 4, exclusive OR data 5, exclusive OR data 7. But I'm just going to pick a side. I'm going to go left to right in terms of this. So if I figure out 0 exclusive OR 1, well, remember the idea in exclusive OR, they have to be different. Well, 0 and 1 are different in order for it to be true, so that is a 1. So the result of this is 1. So now we'll do the 1 exclusive OR 1. Well, they're not different, so this is 0. 0 exclusive OR with 0. They're not different, so this is 0. 0 exclusive OR with 1. It is different, and so that's 1. So check bit 1 is will be check bit 1 is going to be the value 1. Okay, let's move on to check bit 2. So again, let me figure out the for check bit 2, there's a 1 in the 2 to the 1 position. So for all of the data bits that have the 1 in that position, they will be included. That's a little squiggly line. So check bit 2 is going to be data bit 7, exclusive OR data bit 6, exclusive OR data bit 4, exclusive OR data bit 3, exclusive OR data bit 1. Okay, filling in the bits, well, data bit 7 is 0, data bit 6 is 1, data bit 4 is 1, data bit 3 is 0, data bit 1 is 1. So I'll just go left to right. So I lost my mouse. 0 exclusive OR 1, well, they have to be different. Those are different, so this is 1. 1 exclusive OR 1, they're the same, so that's 0. 0 exclusive OR 0 is 0. 0 exclusive OR 1 is 1. So check bit 2 is 1. Okay, going on to check bit 4. Again, I'm going to use the same process. Check bit 4 has a 1 in the 2 to the 2 position in terms of its in terms of its position. So there's a 1 here, there's a 1 here, there's a 1 here, and there's a 1 here. So check bit 4 is going to be data 8, exclusive OR data 4, exclusive OR data 3, exclusive OR data 2. Filling in the bits, data 8 is 0, data 4 is 1, data 3 is 0, data 2 is 0. So 0 exclusive OR 1 is 1, 1 exclusive OR 0 is 1, 1 exclusive OR 0 is 1. So check bit 4, the check bit is 1. Okay, so moving on to check bit 8. Check bit 8, okay, I've lost my mouse. You guys can see it. There we go. Check bit 8 has a 1 in the leftmost position. And all of these data bits have a 1 in the leftmost position. So check bit 8 is going to be data 8 exclusive OR data 7 exclusive OR data 6 exclusive OR data 5. Filling in the bits, so 0, 0, 1, 1, and now let's go and do the calculation. So 0 exclusive OR 0 is 0, 0 exclusive OR 1 is 1, 1 exclusive OR 1 is 0, so check bit 8, then the value comes out to be 0. So the initial 8 bits that we started with, if we were going to write that to memory, the additional check bits that we calculated, check bit 1, check bit 2, check bit 4, check bit 8, those would also be written to memory as well. Later when memory is read, so when we want those 8 bits back into memory, 12 bits are going to be read from memory, 8 of them being the data, 4 being the check bits. What the checker will do is it will calculate what the check bits should be, and then it will compare what the check bits should be to compare to what came from memory. If the check bits match, then we have our data. If the check bits don't match, it will then go and do error correction to figure out which of the data bits that it needs to flip. Okay, so that's Hamming code for 8 data bits with 4 check bits. This sample I just went through is the same sample that's in the demo, the supplement, the addendum for Chapter 5 in Canvas.